Okay, I want you to just close your eyes for a second. Imagine you're driving a car. You're on a highway. It's late at night, pitch black, and your foot is just floored.
And when you say floored, we're not just, breaking the speed limit a little bit.
No, not at all. In this car, you are moving at 110 kilometers per second.
Wow.
That's about 68 miles per
Yeah.
second. You could cross the entire Atlantic Ocean in, like, the time it takes to sneeze.
Which is a terrifying thought, but okay, go
So
ahead.
you're doing this impossible speed, and you look out the windshield. Way, way off in the distance, you see a pair of headlights, and they are not staying in their lane.
Oh.
They're coming straight for you. And the driver of that other car, they're also doing 68 miles per second.
So this is like the cosmic nightmare scenario.
It is. And for decades, this has been the story of our place in the universe. Those headlights, that's the Andromeda Galaxy. We are the Milky Way.
And for a long time, the astronomers, our cosmic traffic cops, have basically been telling us, brace yourselves.
Yeah. That crash, it's not an if, it's a when.
Right. The Andromeda Milky Way collision, it's probably the most famous future event in all of astronomy. The two heavyweights of our local group.
It's just smashing
A
together.
total demolition derby.
And we had a date circled on the calendar for it, didn't we?
We did. The
Yeah.
general consensus was roughly 4.5 billion years from now. It was practically a settled fact.
But, and this is why we're doing this deep dive today, something huge happened last year.
That's right. A real paradigm shift.
We're recording this, for context, on January 29th, 2026.
Yeah.
And if you maybe missed the news out of mid-2025 because you were, I don't know, busy with everything else,
Which is understandable.
let me fill you in. The entire narrative has changed. It turns out that cosmic car crash, it might actually be a near miss.
It's such a classic case of science correcting itself,
Yeah.
as our vision gets sharper. We went from certain doom to, well, a literal coin flip.
So today, we are unpacking the whole Andromeda Milky Way collision story. We're going to look at the new science, that pivotal study from June 2025 that really changed everything.
And we'll get into how you even measure the speed of a galaxy that's millions of light years away, which is, a lot harder than just pointing a radar gun at it.
And we have to talk about what happens if we do crash, because I think we all have this Hollywood movie version in our heads, right? Explosions, planets cracking in half.
And the reality is, well, it's so much weirder.
Weirder how?
It involves ghosts, supermassive black holes, and just a mind-boggling amount of empty space.
And finally, of course, the big question, the fate of our solar system. Because it turns out, even if the galaxies miss each other, things are still going to get very, very hot for us here on Earth. So let's dive in.
Let's do it.
Okay, so I want to start with the before, before last year, before this new study. Just how sure were we that this collision was a done deal? Because in science, you almost never hear the word certain.
That's true.
Yeah.
It's almost always a game of probabilities. But if you rewind to around 2012, the confidence level on this was incredibly high. It was treated as fact.
And this was all based on Hubble data, right?
Exactly. Back in 2012, a team used the Hubble Space Telescope to measure the motion of stars inside Andromeda. And to really appreciate why things changed in 2025, you have to understand just how incredibly difficult that 2012 measurement actually was.
Okay, walk me through it. I get that we can tell if something is moving toward us pretty easily.
Right. That's let's call it the easy part. We use the Doppler effect. It's the same reason an ambulance siren sounds higher pitched when it's coming at you and lower when it's driving away.
Blue shift and red shift for light.
Precisely. If something's moving toward us, its light waves get kind of squashed together, shifted toward the blue end of the spectrum. And Andromeda is very, very blue in that sense. We've known for ages it's closing that gap at the 110 kilometers per second you mentioned.
So, okay, we know it's coming straight at us. Why isn't that enough to predict a crash?
Because of the sideways motion, what we call tangential velocity. Imagine you're standing on a baseball field. A pitcher throws a ball directly at your face.
I would prefer not to, but fine.
You can see the ball getting bigger as it approaches. That's the radial velocity, the blue shift. But if that ball is also moving just a tiny bit to the left, say an inch per second sideways, it's going to completely miss your nose and just whiz right past your ear.
Right, but from 60 feet away, that little bit of sideways movement is almost impossible to see.
Exactly. Now imagine the pitcher is 2.5 million light years away.
Okay, yeah, I see the problem now.
Trying to measure the sideways drift of Andromeda is like, it's like trying to spot a human hair growing on the moon from here on Earth. The precision required is just agonizing.
So how on earth did they do it in 2012?
They used Hubble to track the positions of a whole bunch of stars inside Andromeda, but they measure them relative to even more distant background galaxies.
Background galaxies.
Quasars, mostly. These things are billions of light years away. So for our purposes, they are completely frozen in place. They're like the fixed lighthouses on the distant horizon.
So they looked at Andromeda's stars and just checked if they were drifting left or right compared to those cosmic lighthouses.
Pretty much, yeah. They averaged the movement of thousands of stars over several years to get what they called sub-pixel accuracy.
Sub-pixel. That sounds intense.
It's the absolute limit of what was possible. And the finding back in 2012 was that Andromeda's sideways motion was tiny, almost negligible.
He's coming right for our nose.
Just straight down the middle. So the prediction was a full-on merger in about 4 to 5 billion years.
Okay, so that was the gospel for more than a decade, the Great Collision. Then June 2025 happens, till Sawala and his team publish a study, and boom, everyone's rewriting the textbooks. What did they find? Did they just prove Hubble was wrong?
Well, it's not that Hubble's data was wrong. The data was good. It's that the model they were using was, well, too simple.
Too simple. I mean, we're talking about the physics of entire galaxies. How simple can it be?
Well, the 2012 calculations were essentially what we call a two-body problem. They were just looking at the Milky Way and Andromeda as if they were the only two important things in the universe.
Like 2 billiard balls on a totally empty pool table.
Exactly. But the pool table isn't empty. Far from it. We live in a place called the local group, which is a whole cluster of galaxies. And we have some pretty significant neighbors.
And who are the main players here?
The two big disruptors in the math are the Triangulum Galaxy, that's also known as M33, and the Large Magellanic Cloud.
I've definitely heard of the Magellanic Cloud. If you're in the southern hemisphere, you can just see it in the sky, right?
Yeah, it looks like a sort of detached, cloudy piece of the Milky Way. It's a satellite galaxy of ours, but it's massive, has a lot of gravitational pull. And Triangulum is the third biggest galaxy in our whole local group.
Triangulum. It sounds like a secret society that runs the universe.
It kind of does.
Yeah.
But in this story, it's really just a gravitational bully. What Sawala's team did was use new, incredibly precise data from the Gaia spacecraft combined with Hubble's, and they finally accounted for the mass and gravity of these neighbors.
So they added the other players into the simulation.
They moved from a two-body problem to an n-body problem. And in physics, n-body problems are famous for one thing, chaos.
As in, like, mathematical chaos.
Exactly. Extreme sensitivity to the starting conditions. The Large Magellanic Cloud and Triangulum are constantly tugging on both the Milky Way and Andromeda. They're warping space-time. They're pulling on the trajectories.
If we go back to the baseball analogy, it's like a sudden gust of wind catches the ball mid-flight.
Or like there's a giant magnet buried in the pitcher's mound that just curves the path slightly.
Mm-hmm.
When Sawala and his team ran these new, much more complex simulations with all that extra gravity factored in, that straight-line head-on collision just, it disappeared.
And what was left?
A coin flick.
A literal 50-50.
Almost exactly. The new statistics show there's now about a 50% chance that no collision will happen at all within the next 10 billion years.
That is just, it's wild. We went from this is absolutely happening to maybe, maybe not.
It really is a perfect example of that uncertainty principle in cosmology. We're dealing with such immense scales that one missing variable, like the gravitational pull of the Large Magellanic Cloud, can swing the entire prediction from certain doom to we might be okay.
So there's a real chance we might just wave hello as Andromeda sails by.
A cosmic drive-by, yes. It would still be gravitationally interesting. It'd be close, but not a merger.
That's a huge relief. But, you know, I have to be the one to ask the fun question now. Let's look at the other 50%. Let's say the coin lands on collision.
It's a crash.
A crash. Because when I hear galactic collision, my brain just pictures absolute, total carnage, stars smashing into stars, planets getting knocked around like billiard balls.
And that's a very natural image to conjure up. But it brings us to what I like to call the empty space paradox.
Okay, what's that?
That a galactic collision is actually more of a ghost through.
A ghost through. What does that mean?
It means that if these two galaxies collide, the probability of even a single pair of stars, just two stars, physically hitting each other is practically zero.
Wait a minute. You have to back that up. Andromeda has, what, 1 trillion stars? We have 300 billion? You smash 1 trillion things into 300 billion things and nothing hits.
It's extremely unlikely, yes. And it all comes down to scale. Our brains are just not wired to understand how incredibly empty space actually is.
Give me an analogy. Help me visualize it.
Okay, let's use the one from the source material because it really, really nails the scale perfectly. I want you to imagine that our sun is a single ping pong ball.
Okay, got it. One ping pong ball.
Now, where do you think the nearest star, Proxima Centauri, would be on that scale? If the sun is a ping pong ball right here, is Proxima Centauri across the room, maybe across town?
I feel like this is a trick question, so I'm going to guess. A few hundred miles away?
If the sun is a ping pong ball sitting in London, then Proxima Centauri is a single P in Berlin.
What? No way.
Yes, that's about 1,100 kilometers or 680 miles.
So you have one ping pong ball and then absolutely nothing for almost 700 miles, and then you find one P.
That's it. The average distance between stars in our galaxy is about 160 billion kilometers.
So it's basically just empty space.
Mostly empty space. So a galactic collision is like taking two giant swarms of ping pong balls, where each ball is hundreds of miles from its neighbor, and just passing them through each other.
They just fly right through the gaps.
They fly through the gaps, the galaxies pass through each other like ghosts, the overall structures merge, and the orbits of stars get all scrambled up. But the physical objects, the stars themselves, they almost never touch.
That is fascinating, but I have to admit it's also a little disappointing. I was really expecting some fireworks.
Oh, don't worry. There will be fireworks.
Yeah.
Just not from the stars.
Okay, so if the stars don't collide, what does?
God.
The gas.
Galaxies aren't just stars and planets. They are filled with these massive sprawling clouds of hydrogen gas. We call it the interstellar medium. And unlike stars, which are basically tiny points, these gas clouds are huge and diffuse.
So they can't possibly miss each other.
They can't. When the galaxies start to merge, these gas clouds will slam into each other at supersonic speeds. It creates these enormous shock waves. The gas gets compressed. And what happens when you compress huge amounts of hydrogen gas?
You get new stars.
You get millions and millions of them. We call it a starburst event. The collision would trigger this incredibly furious era of star formation. The sky wouldn't be dark. It would be ablaze with brilliant, hot, blue, newborn stars.
And supernovae going off like popcorn.
Exactly. It would be the single most spectacular light show in the history of the local group.
So the stars don't actually crash, but the cosmic nursery explodes with new life.
That's a great way to put it. But there is a much darker side to this merger. We have to talk about the monsters lurking in the centers of these galaxies.
You mean the black holes?
The supermassive black holes.
Right. We have Sagittarius A star at the center of the Milky Way.
Which is something like 4 million times the mass of our sun.
And what about Andromeda?
Andromeda has a much, much bigger beast in its core. We're talking somewhere between 100 to 200 million solar masses.
So our black hole is a Chihuahua, and theirs is a giant Rottweiler.
A very, very large Rottweiler, yes. And unlike the stars, these two black holes will find each other.
How, though? If all the stars miss, how do the black holes manage to meet up?
It's a process called dynamical friction.
Okay, unpack that for me. Friction in empty space.
It's a great name for it. Think of the black hole as a really heavy bowling ball moving through a sea of marbles, the stars. As the black hole moves, its gravity tugs on the stars, pulling them towards it. It kind of slingshots them, giving them a kick of extra speed.
Okay, so the stars get faster?
But energy has to be conserved, right? So if stars gain all that kinetic energy, the black hole must lose it. It slows down. It loses its orbital momentum.
And so it sinks.
It sinks down towards the new center of mass. Both black holes will do this, spiraling inward closer and closer in this kind of gravitational dance. And when they get to within about 1 light year of each other, that's when reality itself starts to break down.
Gravitational waves.
Massive ones, rippling the very fabric of space-time. And eventually, after losing all that energy, they merge.
And what happens when a 4 million solar mass black hole gets eaten by a 100 million solar mass black hole?
You get a quasar, or what's called an active galactic nucleus.
In plain English.
A cosmic blowtorch. The merger and all the gas that gets funneled down toward it during the chaos, it releases an absolutely ungodly amount of energy. The light from it could outshine the entire rest of the galaxy combined.
So the center of this new galaxy basically becomes a death zone of high-energy radiation.
For a while, yes. It could release as much energy as 100 million supernova explosions.
100 million, that's a number that my brain just can't really process.
It's basically a beacon that screams, "We are here," to the entire observable universe.
Okay, so we've got ghost stars passing through each other, we have exploding gas nurseries creating new stars, and we have a central quasar that melts everything nearby. This leads to the most important question of all, really. Where are we in all of this mess?
The fate of the solar system.
Exactly. Do we get a front row seat? Do we get crushed or incinerated?
Well, the good news is We almost certainly don't get crushed. The whole ping pong ball rule applies to us too. No star is going to get close enough to hit the sun.
Okay, that's good.
But our cosmic address is definitely going to change. There was a study, I think it was back in 2007, from the Harvard-Smithsonian Center that ran simulations on this.
And what did they find?
It's orbital chaos, basically. There's about a 50% chance that during the merger, our solar system gets flung way out into the galactic suburbs. We could end up 3 times farther from the core than we are now.
So we retire to the country.
It'll be a lot darker, much quieter, fewer stars in the night sky. But there's another possibility, a 12% chance.
And what happens in that 12% timeline?
We get ejected.
Ejected, you mean? Like kicked out of the galaxy entirely?
Thrown out completely. We'd become a rogue solar system, cast adrift in the vast, empty intergalactic void.
Just floating, alone.
In the dark. All alone. Over millions of years, the new galaxy would shrink until it's just a faint smudge of light. Eventually, the night sky from Earth would be perfectly, terrifyingly black. No stars, just our sibling planets.
That is a profoundly lonely image.
It is, but, and this is the amazing part, it wouldn't actually harm the solar system itself.
The Earth just keeps orbiting the sun.
Just fine. The gravity binding Earth to the sun is incredibly strong and very local. The huge, tidal galactic forces that scramble the star's orbits, they just aren't strong enough to rip our solar system apart. We'd be a lonely little system, but we'd be intact.
So, in theory, if humans or whatever we evolve into are still around, we could actually survive being ejected.
Physically, yes, you could survive.
So I'm picturing this future civilization, right? They're standing on Earth 4.5 billion years from now. They look up. They see Andromeda getting bigger and bigger in the sky. They see the collision, the starburst. It must be the greatest show in history.
It absolutely would be. But I have to be the bearer of some bad news here.
Oh no, what now?
No one is going to see it.
Why not? Because we'll have gone extinct.
Not just us, the entire planet will be uninhabitable. And the crazy thing is, it has absolutely nothing to do with the collision. Andromeda is completely innocent in this part of the story.
So who's the culprit?
Our own star. The sun.
But I thought the sun was stable for billions of years.
It's stable, yes, but it's constantly evolving. The sun is fusing hydrogen into helium in its core. That's what makes it shine. But as that helium ash builds up, the core gets denser. And because it gets denser, it has to get hotter to maintain equilibrium.
And a hotter core means the sun burns brighter.
Exactly. The sun's luminosity is actually increasing by about 10% every billion years.
10% doesn't sound like a planet killer.
Oh, it is when you're this close. In about 500 million to 1.5 billion years, so long before Andromeda gets here, that slow increase will be enough to trigger a runaway greenhouse effect on Earth.
You mean like what happened on Venus?
Exactly like Venus, but starting from a much nicer place. The oceans will begin to evaporate. And because water vapor is a powerful greenhouse gas, that traps more heat, which causes more evaporation. It's a vicious feedback loop.
And the end result?
The oceans boil away completely. The atmosphere becomes this thick, choking blanket of superheated steam. Surface temperatures will be hundreds of degrees.
So all life on Earth?
Gone. Sterilized. Wiped out.
That is such a sobering reality check. We're all sitting here worrying about this galactic car crash 4 billion years away, but our own engine is going to overheat and cook us in just 1 billion.
It really does put everything in perspective, doesn't it? Unless our distant descendants figure out some kind of incredible planetary engineering like physically moving the Earth farther away from the sun, the Great Collision will happen to an empty dead rock.
Wow. Okay, well that's depressing. But let's zoom out again. Let's assume some civilization is watching this whole thing. Maybe from Titan or a different star system.
Yeah.
After the chaos settles down, what's left?
The aftermath. We get a brand new single galaxy.
And it has a name, doesn't it? A nickname.
It does. Milkomeda.
Milkomeda.
Or some people prefer Milkdromeda.
I gotta be honest, I hate both of them. Milkomeda sounds like a new type of candy bar. Milkdromeda sounds like a medical condition.
Astronomers are not always poets, that's for sure. But whatever we call it, the shape of Milkomeda will be completely different from what we know today.
Because right now, the Milky Way and Andromeda are both these beautiful spiral galaxies. They have flat disks, those graceful arms.
But spiral structures are incredibly fragile. When you smash two of them together, the gravitational chaos completely randomizes all the star orbits. You destroy the disk, you erase the arms.
What do you get instead?
A blob.
A blob.
Well, technically, it's a giant elliptical galaxy. Instead of a flat pancake, it's shaped more like a football or a sphere. It's just a giant, disorganized swarm of stars buzzing around the center in every which direction.
So no more Milky Way bands stretching across our night sky, just a sort of general glow.
Probably a reddish glow, actually.
Uh,
Elliptical galaxies are usually full of older, redder stars because all that gas got used up in that big starburst light show we talked about.
So Milkomeda will be a giant, red, fuzzy football floating in space.
With a supermassive black hole for a heart.
And what about our third wheel, the Triangulum Galaxy, M33? We said it messed up the collision math, but what actually happens to it during all this?
Yeah, M33 is the little sibling trying to tag along. The simulations on its fate are all over the place. Some show it orbiting the new Milkomeda for a few billion years before it finally gets pulled in and merges too.
A delayed snack for the new giant.
Others suggest it might actually hit the Milky Way before Andromeda even gets here. Or, in all the chaos, it might just get slingshotted out of the local group entirely.
It really seems like the ultimate destiny of our local group is just consolidation.
That's the long-term trend. Gravity is relentless. Over the next 100 or 150 billion years, all the major galaxies in our group will likely coalesce into this single massive object.
One giant island in the universe.
And that leads to a really strange thought about the very, very far future.
Go on.
You know about dark energy, right?
The force that's pushing the universe apart, making it expand faster and faster.
Right, so it's making the space between galaxy groups expand. Eventually, all the other galaxies outside our local group will be receding from us faster than the speed of light.
Which means their light can never reach us. They'll disappear from view.
Completely. So imagine a civilization born on a planet inside Milkomeda, say 150 billion years from now. They invent telescopes. They look up, they'll see all the stars in their own galaxy. But if they look deep into intergalactic space, they will see nothing. Absolutely nothing.
Because everything else will have been pushed over the cosmic horizon.
Exactly. They would logically conclude that Milkomeda is the entire universe. They would have no evidence that other galaxies ever existed.
Wow. We are living in a really privileged time, aren't we?
We are living in the golden age of cosmology. We can still see the neighbors. We can measure the expansion. We can reconstruct the history of the Big Bang. In the far, far future, that history will be erased from the sky.
That's heavy, but also kind of beautiful.
It is.
So let's bring this all back home, back to today, to January 2026. What's a big takeaway for someone listening to this right now?
I think the takeaway is that science is a living, breathing process.
What do you mean?
Well, back in 2012, we had what felt like a certainty. The crash is coming. Then in 2025, we got better data, better tools, and we realized the universe is a bit more complicated. And that certainty became a probability.
The coin flip.
The coin flip. It's a great reminder that even when we think we have the future all mapped out, one missing variable, like the gravitational pull of a nearby galaxy, can change absolutely everything.
And even if the coin lands on Collide, it's not death. It's transformation. It's this ghostly dance that ends up creating billions of new stars.
That's a lovely way to see it, yeah.
So here's my final thought for everyone listening. Tonight, if it's a clear night, go outside. If you can get away from the city lights, try to find Andromeda.
It's just a faint, fuzzy patch in the constellation Andromeda. You might need binoculars, but you can find it.
Find that little smudge. And just take a moment to realize that the light hitting your eye left that galaxy 2.5 million years ago. That was before modern humans even existed on this planet.
And as you look at it, remember that it's either rushing toward us for a hug, or maybe it's just rushing past to wave hello.
And thanks to the Triangulum Galaxy, it might just be a friendly wave.
Let's hope for the wave.
Yeah.
It would make for a much quieter neighborhood.
Indeed. Well, that's all the time we have for this deep dive into our galactic future. We hope you feel a little more informed about our impending, or perhaps not so impending, cosmic fate.
And as always, keep looking up.
We'll see you next time.